Hello, I'm Michael Grabus, and my final project is a topology optimization of a Formula SAE race car rear rocker. A bit of background: the suspension on the FSAE car is a pull rod system and it is outlined below. The wheel of the car is bolted onto a hub which can freely rotate with the wheel. The hubs are pressed into bearings that are located on the upright. The upright is the main connection point for all the suspension linkages. The control arms coming off the frame connect to the top and bottom of the upright, and then the push rod which attaches to the rocker also comes off a point on the bottom of the upright. As the wheel vertically displaces, the push rod pushes the rocker and causes it to pivot around the frame mounting point, causing the spring on the shock to compress. As the wheel moves down, the opposite reactions occur. Seen here is a close-up view of the rear right rocker assembly. The goal of this optimization is to minimize the mass of the rocker, since you want the car to be as light as possible, but without compromising the structural integrity and stiffness of the part. This optimization will be set up and run using Altair HyperMesh. The four bolted locations on the rocker are the frame connection, push rod, anti-roll bar, and the shock, all having numbers corresponding to the bolt locations on the diagram. The rocker will be manufactured by Waterjet using a block of 7075 aluminum. The material properties of 7075 are listed here and are input into HyperMesh as a new material. A mesh is created on the rocker in HyperMesh so that the solid can be analyzed. The mesh of choice is a volume tetra mesh. In itself should be fine enough to capture the internal stresses of the part, but ideally coarse enough so that the runtimes are efficient. With the defined cell restrictions, a 3600 cell mesh is created with edge and hole refinements, which are areas that have higher stress concentrations. To properly apply constraints and loading, RBE2 elements are created in the center of each bolt hole. These nodes distribute loading or constraints equally to all dependent nodes located on the interior surfaces of the holes. Load collectors in HyperMesh are chosen as loads and SPC constraints. All of the values in parentheses are the adjusted loadings for a right roll scenario, which the rocker is also subject to in the study, since the rocker sees both right and left roll cases. These loads are for a left roll case. The shock connection is a load of 800 pounds applied into the rocker to mimic the compression of the shock. The anti-roll bar is represented as a 400-pound force directly downward into the ARB mounting hole. The push rod attaching to the right bottom bolt hole is fixed into the vertical direction to represent a static push rod preventing the rocker's movement. Ultimately, a rotational constraint is put on the bearing location where the rocker attaches to the frame. This represents the rocker's rotation about the frame's longitudinal axis. Load steps in HyperMesh couple multiple forces or SPC constraints into a single load collector to simplify the analysis process. A separate load step for right roll and left roll are created, as well as a single load step for the two rocker movement constraints. With these created, an FEA analysis can be run on the part to ensure that the conditions were set up correctly and to ensure that the model is solvable before optimization. With a successful FEA analysis run, the topology optimization setup is created. A topology design variable is created in HyperMesh, having a manufacturing constraint of a single draw, taking into account that the Waterjet process is the chosen manufacturing process. Responses for the optimization are selected as total volume and the static displacement of every single node in the FEA mesh. The optimization objective is defined to minimize the volume response, therefore minimizing mass of the final rocker. A final optimization constraint is defined for the static displacement response. An upper bound of 0.02 of an inch is chosen for both load steps. Shown here is the optimized element density model of the rocker. The video shows all 80 iterations before it converged to the current state. Interesting features that come up with the optimization is the triangulation of the top arched portion of the rocker to the location of the pressed-in bearing, and in the last solution iterations, there are small webs extended from the middle triangulation to the outer two regions of the rocker. These could be crucial for the rocker's performance in buckling, and it'd be interesting to run a buckling analysis with and without these extra parts. This final slide shows the rocker's transformation from its solid shape to the topology optimized model. The solid rocker that only has bolt holes and slots cut for rod ends starts at 1.41 pounds. The element density model is imported into SOLIDWORKS and sketches are drawn onto the basic model so that the cuts shown on the right can be extruded out. The final weight of the optimized rocker is 0.84 pounds, so that is around 40% weight savings of the rocker itself. Since there are two rockers on their car, it equates to over a pound saved for the vehicle, while the rigidity of the rocker is satisfactory to the loading conditions it sees.